presented by Caltech.
Next, I'd like to introduce Kathleen Yang. Kathleen is a sophomore majoring in electrical engineering. She's participated in SURF, and this past summer she worked with Dr. Nei Chang Ye.
Thank you for the introduction. Good afternoon. Today I will be presenting on the growth and characterization of graphene nanoribbons from PECVD and different carbon-based molecules. My mentor was Professor Nei Chang Ye, and my co-mentor was Chen-Je Shu. Today I will be going over an introduction to graphene nanoribbons and their properties and some current synthesis methods. I will also go over the PECVD method. I will then explain the motivation behind this SURF project, and then I will go over the experimental methods and procedure. I will then discuss the results, and finally I will summarize everything. Introduction. Graphene nanoribbons are quasi-one-dimensional crystals. This is due to graphene being a single layer of sp2 hybridized carbon. The quasi-one-dimensional arises from graphene nanoribbons being tens of nanometers wide. Graphene nanoribbons exhibit unique properties such as a high elastic modulus, high electrical and thermal conductivities, high ratio of surface area to volume. This is due to how narrow the graphene nanoribbons are, and quantum confinement, which gives rise to finite energy gaps to otherwise massless relativistic carriers, and many exposed edges, which may be armature or zigzag. If you look at this figure, horizontally are armature edges and vertically are zigzag edges. Some potential applications for graphene nanoribbons are electrode material in batteries and superconductors due to its high electrical and thermal conductivities. Increase the mechanical strength for nanocomposite materials due to its high elastic modulus, and control energy gaps for semiconducting applications, as we can control the energy gap by altering the width of the graphene nanoribbons. Some current synthesis methods are lithography or top-down. This involves cutting out graphene nanoribbons from a sheet of graphene or using lithography. Bottom-up synthesis, which essentially builds up graphene nanoribbons molecule by molecule using chemicals, and unzipping carbon nanotubes. Some issues with these current synthesis methods are that they are expensive, time-consuming, and unsuitable for mass production. So plasma-enhanced chemical vapor deposition, PECVD method, was developed by Professor Ye's group. It involves a carbon-based precursor, transition metal substrate, which might be copper or nickel, for example, and hydrogen plasma, which removes oxide from the surface of the substrate. This allows the substrate to become reactive and catalytic, and this allows the carbon-based precursor to seed upon the substrate and begin to grow the graphene nanoribbons. The schematic can be seen down here. So the motivation behind this SURF project is to explore the possibility of using other carbon-based precursors, such as a solid precursor, to synthesize graphene nanoribbons, to investigate the effects of the processing parameters on the growth of the graphene nanoribbons, and to characterize the properties of the grown graphene nanoribbons. So the materials used were copper foil as our substrate to grow the graphene nanoribbons on. Our precursors were 1,2-dichlorobenzene, 1,2-dibromobenzene, and 1,8-dibromonaphthalene. Their chemical figures are right here, left to right respectively. Some other materials used were hydrogen gas and methane gas. If you look at this schematic, it's of a quartz holder and some copper foils. If you look at it closely, we have the copper foil separated by one position. This is to reduce any contamination that occurs due to prior growth. So here's our experimental setup. So we actually have two different setups for the graphene nanoribbon growth. This is due to 1,2-dichlorobenzene, 1,2-dibromobenzene, and 1,8-dibromonaphthalene not necessarily having the same properties. Some common traits between all of them is the processing tube where the actual growth occurs. We place the quartz holder and the sample inside, and we place a plasma cavity on top. The gas cylinders and the mass flow controls, which we use to control the flow rate of the gas through the processing tube, and the partial pressure, and the power supply, which supplies power to the hydrogen plasma. We also have a cold trap to trap any molecules generated during growth, which might potentially damage the vacuum pump down here. We have some ways of keeping track of the partial pressures during the growth process, such as an optical spectrometer and an RGA. So 1,2-dichlorobenzene and 1,2-dibromobenzene are both liquid precursors. So we can store this inside a container that has a leak valve, and when we open the leak valve, the vapor pressure of the precursor allows it to flow through the processing tube and become involved with the growth. However, 1,8-dibromonaphthalene is a solid precursor, so instead we have to place the precursor inside a boat and place it inside the processing tube and then melt it using a furnace in order for it to interact with the growth process. So the experimental procedure is to clean the copper foils using acetone and isopropanol, then place the copper foils on the quartz holder and inside the PECVD chamber. Then we vacuum the PECVD chamber to 27 millitors, and then we fill the cold trap with liquid nitrogen to trap any molecules that might be going through the processing chamber. And then we fill the PECVD chamber with the hydrogen gas to 500 millitors, and then we grow the graphene nanoribbons with hydrogen plasma powered at 40 watts. Our experimental variables were the growth time, which ranges from 1 minute to 30 minutes, and methane and precursor partial pressure. Results and discussion. So this is an SEM image of the graphene nanoribbons that were grown. They're long and narrow like you would expect graphene nanoribbons to be. An important tool in characterizing the graphene nanoribbons is Raman spectroscopy. This is due to graphene nanoribbons having three very important peaks: the D peak, which is located at 1350 centimeters inverse, the G peak, which is located at 1585 centimeters inverse, and the 2D peak, which is located at 2700 centimeters inverse. Each of these peaks represents a different characteristic of the graphene nanoribbons. The D peak is an indicator of the amount of disorder within the sample, or in this case, the number of edges that the graphene nanoribbons have. The G peak indicates the presence of sp2 hybridized carbon, which is graphene, and the 2D peak gives an indicator of how thick the layers are. So as you can see, the Raman spectra of the graphene nanoribbons grown with 1,2-dichlorobenzene, 1,2-dibromobenzene, and 1,8-dibromonaphthalene all exhibit strong D, G, and 2D peaks, which indicate that the graphene nanoribbons were successfully grown. So we can further use the Raman spectra of the graphene nanoribbons to analyze how the processing parameters affect the growth. This is done by taking the ratios of the D to G peaks and the 2D to G peaks. The ratio of the D to G peak gives an indicator between samples how the number of edges have changed, while the ratio of the 2D to G peak gives an indicator of how the thickness of the samples has changed between samples. So some things to note is that a decrease in the 2D to G peak indicates an increase in the number of layers. A decrease in the D to G peak ratio indicates a decrease in the overall number of edges. This set of graphs compares the growth of the graphene nanoribbons with 1,2-dichlorobenzene and 1,2-dibromobenzene. So you can see for 1,2-dichlorobenzene that the D to G peak ratio stays approximately constant while the 2D to G ratio decreases. The decrease in the 2D to G ratio indicates that the samples were going thicker. This would indicate that the graphene nanoribbons were growing longer, and perhaps new graphene nanoribbons were also being formed on the substrate. For 1,2-dibromobenzene, we see that the 2D to G peak ratio increases while the D to G peak ratio decreases. This indicates that the layers are getting, there are less layers and there are less edges overall. This would indicate that the graphene nanoribbons are growing wider. This is due to when graphene nanoribbons go wider, there's less edges being formed during the growth process. So the difference between these growth mechanisms may be due to 1,2-dibromobenzene having a vapor pressure of 2 magnitudes smaller than 1,2-dichlorobenzene. As a result, this would impact the growth process. This set of graphs compares the growth of graphene nanoribbons with and without methane. For the growth of graphene nanoribbons without methane, we see that the 2D to G peak ratio increases, which indicates that less layers are being formed. This would suggest that the primary growth of the graphene nanoribbons is to grow longer, and there weren't very many new graphene nanoribbons being synthesized. However, for the graphene nanoribbons grown with methane, we see that the 2D to G peak ratio increases while the D to G peak ratio decreases. As I stated before, this indicates that the graphene nanoribbons are growing wider. So this suggests that that methane impacts the formation of the graphene nanoribbons by causing them to grow wider. And when normally the growth mechanism would be that the graphene nanoribbons are growing longer or new graphene nanoribbons would be synthesized. This set of graphs compares the growth of graphene nanoribbons with 1,2-dichlorobenzene and 1,2-dibromobenzene versus time. So for the growth with 1,2-dichlorobenzene, we see between 5 and 10 minutes that there is a drop in the 2D to G ratio and the D to G ratio. This would suggest that new graphene nanoribbons are being synthesized very rapidly as the layers are becoming thicker. And then after that, from 10 to 30 minutes, we see that the D to G ratio increases and the 2D to G ratio increases, which indicates that graphene nanoribbons are continuing to live longer, and also new graphene nanoribbons are being synthesized. However, for the growth of graphene nanoribbons with 1,2-dibromobenzene, we see that the D to G ratio and 2D to G ratio stays approximately constant due to the large error bars. This suggests that the graphene nanoribbons are simply growing longer. So we noticed an interesting phenomenon during the growth of the graphene nanoribbons. We noticed that graphene nanoribbons grown with a smaller proportion of precursor tended to be what you would expect, long, narrow, and tangled with each other, but they're typical graphene nanoribbons. However, graphene nanoribbons grown with a large proportion of precursor and exhibited an interesting phenomenon known as branching. We believe that this is due to the excess precursor saturating the surface of the copper substrate, and as a result, the excess precursor has nowhere else to seed upon. So when the hydrogen plasma interacts with the graphene nanoribbons themselves, this facilitates the attachment of the precursor onto the actual graphene nanoribbons themselves using the halides, and this results in the branching that you can see in this figure. This is supported by the XPS spectra of the graphene nanoribbons grown with a small proportion of 1,2-dichlorobenzene and a large proportion of 1,2-dichlorobenzene. For the graphene nanoribbons grown with a small proportion of 1,2-dichlorobenzene, we see that there are no chlorine peaks, while the graphene nanoribbons grown with a large proportion of 1,2-dichlorobenzene exhibit chlorine peaks, which indicate that the halides are somehow facilitating the attachment of the precursor onto the graphene nanoribbons when they branch. We saw a similar phenomenon for graphene nanoribbons grown with other precursors. This is 1,8-dibromonaphthalene. We see that with a small proportion of 1,8-dibromonaphthalene, which occurs when there's a lower temperature, so it melts at a slower rate, that the graphene nanoribbons are what you would expect them to be. While on the other hand, the graphene nanoribbons grown with a large proportion of 1,8-dibromonaphthalene exhibit branching. Unfortunately, we do not have any SEM images of the branching graphene nanoribbons with 1,2-dibromobenzene. We believe that this is due to 1,2-dibromobenzene having a much lower vapor pressure than 1,2-dichlorobenzene. And as a result, even if we open the leak valve to its maximum, we cannot have an excess amount of precursor within the processing tube, and thus the branching cannot occur. Another interesting phenomenon noticed during the graphene nanoribbon growth is the presence of nanoparticles. If you look at these SEM images of the graphene nanoribbons grown with 1,2-dichlorobenzene, 1,2-dibromobenzene, and 1,8-dibromonaphthalene respectively, you can see in the background there are nanoparticles. We believe this is how the graphene nanoribbons initially form. When the hydrogen plasma first interacts with the copper substrate and removes the oxide, we believe that the precursor comes along, and before actually growing the graphene nanoribbons, they ball themselves up into nanoparticles that you can see in these figures, and then they reside on the substrate until more precursor comes along, and then these nanoparticles begin to unfurl and then grow the graphene nanoribbons. This is supported by the nanoparticles disappearing exponentially with respect to time, with respect to growth time. So here's our summary. Using the PECVD method, the graphene nanoribbons were synthesized as seen by the Raman spectra. Increasing the growth time leads to longer and wider graphene nanoribbons, as well as the formation of new graphene nanoribbons. The presence of methane facilitates the formation of new graphene nanoribbons and also helps increase the width of the graphene nanoribbons. Increasing the partial pressure of a precursor leads to the branching phenomenon that we saw. And branching may be due to the presence of excess halides and the lack of substrate to seed upon. And the halides seem to impact the formation of the new graphene nanoribbons by initially forming the nanoparticles. Acknowledgements. Thanks to Professor Ye for giving me the opportunity to work in her lab and mentoring me. Thanks to Chenja Xu for co-mentoring me and providing the SEM images. And thanks to Dr. Wei-Shun Teng for providing the XPS spectra. And special thanks to the Robert K. and Alice L. Roney Fellowship. Thank you for your attention. Are there any questions?
I would like to open the floor for questions.
Yes.
I guess I had two questions. So at the beginning of your talk, you mentioned armchair versus zigzag for the edge structure of these nanoribbons. Do you have a sense for these ribbons that you're growing here, what I guess are they all armchair or are they all zigzag, or do you have a way to quantify that?
I believe that we've noticed that the graphene nanoribbons that we're growing with this process tend to exhibit armchair edges, which is a good thing because the armchair edges tend to be more stable than the zigzag edges.
How do you guys determine that?
I'm not entirely sure. I believe we use SEM and TEM. I wasn't involved with like actually looking at them using SEM because I didn't have access to the facilities. But my professor and my mentor told me that they tend to turn out as armchair edges. What was your other question?
For thick, do you know what thick, you have these top-down images, do you know how thick your ribbons are?
We don't know how thick they actually are. All I can say is that they're probably around tens of nanometers wide, like I said in the introduction.
Okay. Any other questions? I'd like to thank you.